let's suppose that we have a person on a bicycle carrying a tuning fork, and that tuning fork is going to emit sound at a frequency of 461 hertz. And that bicycle is going to be with some velocity approaching a wall. And we're going to hear a beat frequency of 5 hertz as we approach the wall. So that's from the echo of the tuning fork. That means the echo is off by 5 hertz. So I want to know, can we figure out what the velocity of the bicycle over here with the tuning fork on it was? If I look in section 13.9 of your book, it gives me some important facts. First of all, it says if there were a person standing over here listening to the sound, they would report hearing a frequency greater than the one emitted. So if we have stationary observer approaching source, those sound waves get squished together by the person moving, and so we have a higher frequency observed, which means the echo we hear back should have a higher frequency observed. That's important because if we're dealing with beat frequency, we could go up 5 or down 5 from our original sound, and this means we go up 5. So we know that we were hearing a 466 hertz sound interacting with our 461 hertz sound emitted from the tuning fork. Well, what can I do with that? In that same chapter in your book, it gives me a formula for an observed frequency if I'm approaching the stationary source, so the guy over here. And that is, let's turn to section 13.9, F observed equals the velocity of sound over the velocity of sound minus the velocity of the source. So you might think, okay, well it's time to just plug these in, times my frequency. But what would, this equation only works for source approaching stationary observer, which isn't quite right because the bicycle is moving too. So this is going to be symmetric. The bicyclist is approaching the wall for the sound emitted this way, and when it comes back, we could say the wall is approaching the bicyclist. So it's a symmetric effect, which means it's getting doubled. So really, the person over here would hear a frequency only 2.5 hertz higher. So our observed frequency is only going to be 2.5 hertz higher because that's what this person would hear. Again, that's just because the effect is symmetric. It goes this way, adds 2.5 hertz, goes this way, adds 2.5 hertz. To get that 2.5, I'm just dividing my beat frequency by 2 because I know it happens both ways. So my observed frequency then is at the wall. So if I'm at the wall, 463.5 hertz. Now that I know that, the only thing I don't know is my V source, so I can solve for that. So let's just solve this equation for V source. And if I solve this equation for V source, I'm going to do Vs minus V source times F observed, Vs times F. And now I've got to get V source by itself. And therefore we have V source equals Vs minus Vs over F observed. So now I plug in my numbers. I'm looking for V source. I don't know it. Speed of sound in air we can look up. It's 343 meters per second minus 343 meters per second times my emitted frequency, 461 hertz, over my frequency that I heard if I were standing at the wall, 463.5 hertz. And if I do all this, I find that the bicycle's speed is 1.85 meters per second. That section of the book, 13.9, has a lot of pictures and is actually really helpful. So if you're having trouble with a problem like this, I suggest going to that section and reading it. There are some great pictures and great text.